Recording. Okay. So good afternoon, everyone, and welcome to this seminar, which is organized by UNSW and is also part of statistics across campuses. So today we have Pavel Krupskiy as our speaker. So Pavel is a lecturer at the University of Melbourne, and his research focuses on dependence modeling for a multivariate case and also the tail dependence modeling. So today, Pavel is going to talk about conditional, normal, extreme value copulas. The floor is yours, Pavel.
Okay, so thank you very much for the introduction. So yeah, so the title of my talk, yes, it's a conditional, normal, extreme value copulas. So this is joint work with Mark Genton from King Abdullah University of Science and Technology. So here's some outline of my talk. So I'll start with some introduction. I'm going to explain a little bit what copula function is and why it's useful in modeling multivariate data. So I'm going to define a multivariate extremes and extreme value copulas. Then I'm going to focus on a special class of models called conditional normal extreme value copulas. I consider their tail properties, special cases that results in parsimonious dependent structures. Then I'm going to talk about parameter estimation and empirical study. And then I'm going to conclude my talk. Okay, so what is a copula? Copula is simply a multivariate distribution function with uniform 0, 1 marginals. So for any continuous multivariate distribution function f with marginal distribution functions f1, fd, there exists a unique copula C that links these univariate marginals f1, fd into multivariate distribution f. So alternatively, you can define copula as the function as the CDF, the joint CDF of univariate quantiles. So copulas can help construct a flexible multivariate distributions with arbitrary marginals. So sometimes in applications, you know what the marginals should be, and you want to develop a very flexible model for the multivariate dependence. And you can use this a nice result that you can get the copula that actually links these multivariate univariate marginals into multivariate distribution function. So properties of copulas. So there are some desirable properties depending on the application. So let's talk about some basic properties that might or might not be plausible in different cases. So assume that we have a divariate random variable u1, ud, and we assume that the marginals are uniform. So that's why the joint CDF cumulative distribution function is a copula. So we denote this copula as C with the subscript 1d. So a reflection symmetry of the copula is called a reflection symmetric if the joint distribution of the vector u1, ud is the same as the joint distribution of the reflected vector. So 1 minus u1, 1 minus ud. So again, you can think of copula as the multivariate distribution of quantiles. So the distribution is called reflection symmetric if the probability of observing lower quantiles is the same as the joint probability of observing upper tiles. For example, if you have a bivariate random variable, the probability that both random variables take value below the respective 1% quantile is going to be the same as the probability that both variables exceed the respective 99% quantiles. So this is what we call the reflection symmetry property. Permutation symmetry property is when the order of variables is not important. So the distribution of u1 is going to be the same as distribution of u2, u1. So you can change the variables. So for any permutation sigma here on the slide, the distribution of sigma u sigma 1 u sigma d is the same as the distribution of u1 ud. Also, you can define the concept of a lower and upper tail dependence to measure the strength of dependence in the joint tail. So you can define it for a pair of variables. So let's assume that we have a pair of uj, uk. So two variables uj and uk. So you can define the lower and upper tail dependence coefficients as the limits. So the probability that uj takes value smaller than q quantile, and that variable uk takes a value smaller than q quantile, and you assume that this q goes to 0. So if the limit exists and it's positive, then we say that the pair uj-uk has positive lower tail dependence. Similar with upper tail dependence. So what that means? It means that two variables, uj and uk, they're asymptotically dependent in the tail. So when both of them take very small values, they're still dependent. Actually, there are some distributions when two variables are dependent, for example, bivariate normal distribution with a positive correlation, which is smaller than 1. Then these two variables are dependent, but they are tail independent, which means that if you consider very small quantiles of a bivariate normal random variable, they become asymptotically independent in the tail. And a similar idea with the upper tail dependence, but when you consider upper quantiles instead of lower quantiles. So copulas can be used to model a lower and upper tail dependence, which might be important when your variables have very strong dependence in the tail, which cannot be captured by a standard normal model, for example. So here are some bivariate scatter plots for normal copula on uniform scale. So assuming that all marginals take value, the marginals take values between 0 and 1. So you could see here that it's pretty symmetric. So it's asymmetric with respect to the main diagonal and also side diagonal, which means that this distribution is permutation symmetric and reflection symmetric. So the joint occurrence, the probability of joint occurrence of two small quantiles or two big quantiles is the same. So for the T copula, student T copula with 3 degrees of freedom, you see the pictures kind of look similar, but the points in the lower and upper quantiles, in the lower and upper corners of the unit square, you see maybe a little bit more points in there. So dependence is a bit stronger, and in fact this copula has lower tail dependence and upper tail dependence. Also, you could see that you see some points around 0, 1 and 1, 0 corners, unlike normal copula. For normal copula, you don't see any points actually close to these corners, 1, 0 and 0, 1 corner. So there is a small difference between these two copulas actually. But if you consider some other copulas like Gumbel copula, you could see there is a big difference now between these two copulas and the Gumbel one, because you can clearly see that this distribution is asymmetric. In the upper tail, the points, you see a lot of points close to the main diagonal, but in the lower tail, the points are really scattered. So the dependence is much weaker. The joint dependence between U1 and U2 is much weaker in the joint lower tail for this copula. For the Clayton copula, it's another asymmetric copula. We have the opposite. So the joint dependence in the joint lower tail is much stronger than the joint dependence in the upper tail. Well, this is just for a bivariate when you have two variables. Of course, these ideas can be extended to multivariate copulas. It's just easier to visualize it in bivariate case. So, okay, so let's talk now about multivariate extreme value distributions. So assume that we have n independent identically distributed random vectors, u1, un. So each random vector has d components, so it's a d-variate vector. And we assume that the distribution of this vector is given by a copula, which we denote again C1d as before. So we consider the vector of component-wise maxima. So we have a sample of size n, and then we just take component-wise maxima. So we get a new vector of length d. So assume that there exist a normalizing constants an and bn such that after you properly rescale this component-wise maxima, then this vector will converge in distribution to some non-degenerate multivariate distribution. So let's assume that it's converged to a vector which we denote U infinity, which has a non-degenerate distribution. Then we say that the vector U infinity is the extreme value limit of the sequence UN. So again, we started with uniform marginals for a vector UI. So the components of the vector UI, we assume they have uniform marginals. Again, because we are doing it on a Copula scale, we are not interested in marginals. So we assume everything is transformed to standard uniform marginals. But once you take the limit, the marginal distributions of the U infinity are not necessarily uniform. In fact, they will not be uniform. But again, this is not important for this talk. What is important actually is the copula that corresponds to the distribution of this vector U infinity. So the copula of the extreme value limit is called extreme value limiting copula, and we denote this copula by CEV. So we're going to use this notation for this copula. It's easy to check that if we start with the copula C1D, and then we take component-wise maxima, and then we assume the limit exists, then the extreme value limit in copula can be expressed as the following limit in terms of the original copula as n goes to infinity. Of course, provided that this limit here exists. So why use extreme value distributions? Well, this class of models is very useful for modeling multivariate extremes. For example, when you have a portfolio of stocks and you want to do some analysis of stock return maxima or minima. For example, as an investor, you might be interested in the estimating the joint distribution of a portfolio, the components, minima of portfolio components, stocks in particular. So this can help you to estimate predicted loss of your portfolio, because minima means you have unusually a small return of your portfolio. So also in applications in weather, monthly wind maxima might be of interest. So you might have different weather stations located in a certain region, and you might want to check the monthly wind maxima data, and you want to predict the joint distribution of monthly wind maxima to estimate potential damage if you have some extreme event when you have a storm that affects all the stations in the region. Also, you can use extreme value distributions to predict, to estimate the risk of default of certain assets in finance. And there are many more applications, of course. So, so now the good question is how to build a flexible model for multivariate extremes. So we're going to talk about one class of such models, which we call conditional normal extreme value copulas. So we define this model as an extreme value limit of copula C1D. So we assume that they have a vector U, which is a divariate vector, and we assume that the distribution of this vector is given by copula C. We assume that there exists an unobserved factor V0, which has uniform distribution. And we assume that the conditional distribution of the components of this vector U condition on the common factor has distribution which is given by a normal copula with some correlation matrix sigma, when sigma can potentially depend on the conditional value of the common factor. So we have some building blocks in this model. So we assume that the observed variable ui, so the ith component of the vector u, and the unobserved factor v0 is linked together by a copula which we denote I0, CI0. So we call this bivariate linking copula. So we have d components in our vector u, Therefore, we have d bivariate linking copulas in our model. The copulas that link each of the d components to the unobserved factor. So then to find the joint CDF in this model, well, we have to condition on this common factor. Conditional on the common factor, the distribution is given by a normal copula, and then we have to integrate this common factor out. So as a result, we get the CDF, the joint CDF, the unconditional CDF for this conditional normal copula as a one-dimensional integral. So in this talk, we're going to focus on the tail properties and extreme value limits of this class of models. We're going to consider extreme value limit of conditional normal copulas. So let's start with the properties of conditional normal copulas first. So if the sigma matrix, so remember, conditional on the factor, we assume the components of the vector u have a distribution which is given by a normal copula with correlation matrix sigma. So if sigma is an identity matrix, then the conditional distribution is simply an independence copula, because identity matrix for normal distribution implies independence. In this case, the conditional normal copula simplifies to one-factor copula model. So when we have a common factor and conditional on the factor, components of your random vector u are independent. So second interesting special case, when sigma, the correlation matrix, is a matrix of ones, and all linking copulas are actually the same. Then you can check that actually the resulting copula is going to be a comonotonicity copula. So this is the copula when actually instead of d components, we assume that all d components are actually the same. So we have a perfect positive dependence. If all linking copulas are independent copulas, so we actually assume that in that sense that in that case that unobserved factor and observed variables are independent. So this common factor has no influence on the observed variables at all. Then the conditional normal copula becomes simply normal copula with correlation matrix sigma. So normal copula is a special case of this model as well. And now two important tail properties which are useful when we define the extreme value limit of this class of models. If linking copulas have upper tail dependence, in other words, if upper quantiles are dependent in the tail, then the resulting copula has upper tail dependence. So if sigma is a non-degenerate matrix, and linking copulas have no upper tail dependence, then the resulting conditional normal copula has no upper tail dependence. So we're going to use these two properties now. So now we're going to consider two different limits that we can get in this class of models. So assume this assumption here holds in proposition 1. So this function bj given 0 and b not given j are called tail function, conditional tail function. And this is defined as the limiting property, the limiting quantity. So the conditional distribution when actually upper quantiles are considered. So if these limits actually exist, and if these limits are proper CDFs, then they exist an extreme value limiting copula, and in the conditional for the conditional normal model, and this extreme value limiting copula has this exponent function which is given by this integral. So this integral depends on the conditional normal copula. And these tail functions here. So if you know the exponent function, then you can express the extreme value limit in copula as through this exponent function. So essentially, it's sufficient to know the exponent function to recover the extreme value limit in copula. So what these conditions of proposition 1 imply? So if this tail function bj given 0 and b0 given j exist and they are proper CDFs, that implies actually that the linking copula C naught j have upper tail dependence. So you cannot get a proper limit in this model if you use linking copulas without upper tail dependence. So you have to select linking copulas with upper tail dependence to get this type of limit in conditional normal copula model. Okay, so there is another interesting case. Assume now that sigma actually is a matrix of ones, so it's a degenerate matrix. And we assume that the linking copula densities are continuous functions on 0, 1 square, including the upper bound, and positive on the interior of the unit square. So here we assume that the copula density is a continuous function on 0, 1, including the upper bound, which implies that actually these copulas have no upper tail dependence. If copulas have upper tail dependence, then the density is unbounded when the second argument of the copula approaches 1. So the exponent function of the extreme value limiting copula in this case is actually the integral of this maximum of weighted densities, copula densities. So this is the formula here. So this is a very interesting class of models, and actually the support of the copula density in this for this limit is a subset of unit hypercube. In particular, the density is 0 in the neighborhood of the corner 1, 0, 0, for example. This model cannot handle data when you can observe some points arbitrarily close to that corner. So this model is suitable for modeling very strong dependence when the probability of observing values close to the corners of a unit hypercube are essentially 0. Let's consider some special cases that corresponds to a first case when actually sigma is a non-degenerate matrix and we have upper tail dependence copulas. So let's consider first the case of spatial extremes. So assume that sigma, we have this conditional normal copula. So we assume that sigma here has a spatial structure, spatial covariance structure. So in other words, we assume that the covariance is the correlation is smaller if the distance between two measurements is larger. So this is what we call a spatial dependence. So the correlation is a decreasing function with distance. Also assume that we use the same linking copulas. So remember, we have D linking copulas that link each of the D components of the observed vector to the unobserved factor. Then if under certain assumptions, there are some regularity assumptions listed here in proposition 3, we have this result, and important corollary here is that if the correlation as a function of if the correlation is a function of distance, so r here is the distance between two locations in space. So if the correlation approach 1 at rate alpha, if distance goes to 0, then the upper tail dependence coefficient also approaches 1 at rate alpha divided by 2. So this is important relationship between the correlation function and the tail dependence coefficient as a function of distance. So for example, if alpha equals 2, then the correlation function is differentiable at origin, and then we have a smooth spatial process. And in this case, this result shows that the upper tail dependence coefficient approaches 1 at a linear rate. So alpha divided by 2 equals 1. If alpha is smaller than 2, for example, alpha equals 1, so when the correlation function is not differentiable at the origin, this implies that we have a very rough process. And this result shows that we also can control the tail dependence as a function of distance, and the rate is going to be a square root of of the distance. So this type of corollary is useful because then we can control the rate of decay of a tail dependence coefficient with distance. So we know what alpha we should select such that we know such that we fit the rate of decay in the tail if we know how fast tail dependence actually decreases with distance. This might be useful in some applications in spatial statistics. Okay, so let's consider some special case of this class of models for spatial data. So probably some of you know Husler's Copula. This is very popular Copula for modeling spatial extremes. And this is actually a special case of this conditional normal extreme value Copula model. So this can be seen as an extreme value limit of conditional normal Copula that links components of the vector W, W1, WD. So the components of this vector W are defined as the components of multivariate normal vector with some covariance matrix sigma plus a random shift. So V naught here is one factor which has an exponential distribution. You have some fixed weights, alpha j's. And you can see that the joint distribution of W1, WD are given by Copula, which is conditional normal. Because conditional on the factor V naught, the joint distribution of WJs is given by a normal Copula. So, and also you can show in this case that the extreme value limit of this model, extreme value limit of the Copula that corresponds to the joint distribution of components W, is actually Husler's Copula. So another interesting special case is extremal T Copula. Extremal T Copula is defined as the extreme value limit of T Copula with new degrees of freedom. And of course, the T Copula itself can be seen as the conditional Copula. So you remember how a T Copula is defined. So you take multivariate normal distribution, and now you multiply each component by a multiplicative factor, which is inverse chi-square distribution. So essentially, conditional on this multiplicative factor, again, the distribution of components Wj is going to be given by a Gaussian Copula. So that's why we have conditional normal distribution here. So conditional on the factor, the distribution of observed variables is going to be given by a Gaussian Copula. And the extreme value limit of that is extremal T Copula. So that's why extremal T Copula is another special case of this class of models. Another example is a factor structure or dynamic dependence. So sigma might have a factor structure or time variant correlations if you want to model models that have some factor structure dependence or some dynamic dependence. Well, some simple case here is identity matrix. So again, if we assume that variables are conditionally independent given common factor, as I said, it's a special case of a one-factor model. And if you take extreme value limit of that, you're going to get a one-factor extreme value limit in Copula. So these models are suited for modeling data when there exists a single factor that affects the joint dependence of all observed variables. So yeah, so for example, you have weather stations and you want to record monthly wind maxima data. So there might be a common factor, for example, proximity to the sea coast that affects the weather at each of these stations. So and conditional on this factor, you may assume independence among these stations. So and then you consider maxima data, and then the maxima data can be described by this model, one-factor extreme value Copula model. Second special case here, if sigma is a block diagonal matrix, so you have you can partition your data into several non-overlapping groups, and you assume that dependence is stronger within each of these groups, and dependence is weaker if you select variables from different groups. So you have this block diagonal structure for the correlation matrix sigma. Then the respective limit is called bifactor extreme value copula. So this model might be suitable for modeling maxima or minima of log returns of stocks from different sectors. So you can partition your stocks into several sectors. For example, you have an industry sector, you have financial sector, you have consumer staples sector, etc. And of course, stocks from the same sector exhibit stronger dependence, which is a well-known fact. And you also expect that the maxima or minima to follow the same pattern. So dependence among maxima or minima should be stronger for stocks from the same sector, and it should be weaker than for stocks from different sectors. In this case, you can select sigma, which has a block diagonal matrix to model this type of dependence. Okay, so how to estimate parameters in this model? We first consider the case when extreme value limit in Copula is obtained as a limit when sigma has a non-degenerate matrix and link in Copulas have upper tail dependence. So as it often the case with the multivariate extreme value Copulas, the joint density is not available in closed form. And composite likelihood approach can be used instead. So you can consider a JK margin, bivariate margin, and to compute a bivariate likelihood, you need to compute the exponent function and its derivatives, first and second order derivatives of the exponent function, when the exponent function is an integral of this expression here. As you can see, exponent function and its derivatives, well, you cannot compute this integral in closed form, so you need to do numerical integration. And here is the problem, because the integrand here is a slowly decaying function of variable w naught, the integrating variable. So if you try to use some quadrature to estimate this integral using numerical methods, it might not work well, simply because the integral is going down to zero very slowly. And you have this infinite upper bound in the integral. So that's why you need some changes of variables required here to make computation more efficient. So how this can be done? So we change variables. We split this integral into two parts. So the first is just integral from 0 to 1. And we keep it as it is. So we don't change variables in here. We know that the integrand function, if you look at this integral here, is minus a Copula CDF. So it's a bounded function. So it shouldn't be a problem to compute the integral over the finite interval, 0, 1 in this case, for the first part. But then there is a second part from 1 to infinity, and what you're going to do, you're going to change variable w naught here, and you're going to replace it with z naught to the power of negative alpha. Alpha is, after you simplify it, you will see that now we have a finite limits, integration limits, after you change the variable like that. And now you have to select alpha such that the integrand function actually is a finite function. So that you have a finite integrand, and you also have finite integration limits. And this can be done if you select alpha, which is the minimum of these two parameters, Cj and Ck, which actually represents the rate of decay of this tail function. For example, for the reflected Clayton link in Copulas, Psi is just a parameter of the Copula plus 1. For the Gumbel Copula, it's going to be a parameter itself. So it's this is the change of variables. After you do this change of variables, the numerical integration becomes much more stable, and you could use Gauss-Legendre quadrature with 35 quadrature points to compute the Copula density, which is actually a function of this exponent measure and its derivatives with a good accuracy. So after you do that, then you can implement pairwise likelihood approach to estimate parameters in this model. So what about second class of models? So you remember we have two classes of extreme value limits. The second class is obtained when the conditional normal copula has the correlation matrix, which is a matrix of ones. And the linking copulas have upper tail quadrant independence. So essentially the density is continuous function on 0, 1 square. So the likelihood approach here is not suitable, unfortunately, because the support of the Copula density depends on the Copula parameter. And it might not be possible actually to find a region such that the Copula density is positive simply because of the noise that present in your data. So in this case, the likelihood will not work. But what you could do, you could use, you can try to match empirical and model-based estimates of tail dependence coefficient. So for the bivariate margin jk, so when you consider component j and component k of your divariate vector u, you can compute the tail dependence coefficient for this pair. And then you can try to match it with the empirical coefficient. So you can estimate lambda tail dependence coefficient empirically, and you can try to match it with the model-based estimate, which depends of course, on linking parameters on the parameters of the linking copulas. And so actually it's kind of analogous to a method of moment estimator, but here instead of matching moments, we are matching tail dependence coefficients. In fact, it's true that this model is not identifiable and in the general case, and one parameter should be fixed to estimate the remaining parameters. And yes, so this approach also can be used, of course, to estimate parameters of the copula in the first case, when you have a non-degenerate matrix sigma. Of course, the pairwise likelihood is more efficient. But this approach, when you try to find parameters theta j, theta k, such that this sum of squares residuals is as small as possible, is much faster, because you don't have to compute derivatives, you don't have to estimate the likelihood function when you match lambdas. So this is much faster. So there is a trade-off here between speed and efficiency. But for the second case of when you have copulas that corresponds to extreme value limit of the model with the degenerate sigma matrix, you can only use a second approach. Okay, so just some small simulation study. So here just assume that we have a reflected Clayton copulas, dimension 10. And you have a parameter here, first three parameters corresponds to a fairly weak dependence. So remember, the reflected Clayton copulas here are used to link each of the 10 observed variables to the unobserved factor. So first three variables are kind of weakly dependent on the unobserved factor. 4 variables in the middle are strongly dependent with the unobserved factor, and the dependence between observed variables and unobserved factor is weaker, kind of mid-range for the last 3 observed variables. We used Clayton, and reflected Clayton has upper tail dependence. So, so assumptions of proposition 1 satisfied. So we have a non-degenerate limit in this case. So the correlation matrix. So assume that after we condition on the common factor, we assume that we have a normal copula and we have this autoregressive structure for the correlation matrix sigma. So we assume that our correlations are decay exponentially. So if we move away from the diagonal, so if the index j minus k, if this difference is larger than the correlations is weaker. And we assume that we have 0.5 here, the base here for this exponent. And we try 2 methods. The first method is just pairwise likelihood, when we estimate the bivariate density, and then we combine them together in pairwise likelihood and estimate parameters. And method 2 is a matching tail dependence coefficient, which is a faster approach, but it's less efficient. Here, this table below represents the root mean squared errors multiplied by 100 of the parameter estimates theta hat, which is this estimates of this vector theta. And we also have the estimate of the correlation parameter rho, which in this case is 0.5. So if sample size increases, we can see that the root mean squared errors are going down for both methods, as expected. It's good. You also could see that both methods are somewhat less accurate if parameters are, if dependence is stronger between the observed variable and unobserved factor. And we see also, if you compare method 1 and 2, if dependence is quite weak between observed variable and unobserved factor, there is no loss of efficiency. But if a dependence is, I think I kind of flipped that. So it should be method 1 here, not method 2, because method 1 should be more efficient, obviously. So you cannot get a better root mean squared errors for the approximate method. So it's actually method 1 here, the second line here. So for the method 1, these are the root mean squared errors, and you can see they're slightly smaller, especially if dependence is stronger. These two methods, the maximum likelihood approach is more efficient, and it's quite a bit of an increase in efficiency when you estimate parameter rho. And similar, if dimension increases, again, you see that there is a bit of loss of efficiency, maybe 10% on average for theta parameters, and up to 20% for the rho parameter for the fast method. But again, fast method is faster than the likelihood approach. It's maybe 20 times faster. So you can use a fast method, for example, to get some decent estimates of parameters and then use them as starting points for the pairwise likelihood approach, which is more efficient. So yeah, you could use this fast method to get a very good starting points for the pairwise likelihood approach. Here, the second simulation study. Again, we use a reflected Clayton. Now dimension is 20. Instead of 10 variables, we have 20. We have few groups of variables. First group have very weak dependence with the unobserved factor. Second group has a bit stronger. Third group has even stronger dependence, and the last one has a very strong dependence. Also, we have a conditional normal model, and now we have again a autoregressive structure with correlation parameter 0.7 here. Again, you can see that if dependence is weak, there is no loss of efficiency between the two methods. There is no big change, but if dependence is stronger, we start seeing some loss of efficiency, up to 10% for parameter theta for the fast method, and quite a bit of loss of efficiency, up to 20% for the correlation parameter rho. Also, you could see here by comparing these two simulation studies, study 1, this is the magnitude of root mean squared errors for the correlation parameter rho. And this is the, you see that root mean squared error is now smaller. So this is the general pattern that we found in simulation study. If the correlation parameter is, if the residual dependence is stronger, so if the correlation parameter is higher, and if dimension is higher, then we actually can reduce the root mean squared error for the correlation parameter rho. Yeah. So let's now consider some examples with real data sets. So we have wind data. So we consider a monthly maxima of the average daily wind speed for 12 stations in Oklahoma State. So we select 20 years, but we only use 3 summer months, June to August, because the weather patterns are different in winter time. We select reflected Clayton linking Copulas again with the same parameter theta. The correlation matrix here has the powered exponential structure with 2 parameters gamma and alpha, and also nugget effect. So we have 3 parameters for the correlation parameter, correlation matrix sigma. So here is the fit of the model. We see quite a lot of variability. So the black dots here are the estimates of Spearman correlation for different pairs of stations. And you can see there is a decreasing pattern. So the dependence is weaker with distance. So if distance is around 200 kilometers, the dependence in terms of Spearman's rho is around 0.8. and is approaching 0.9 and above if the distance is smaller than 50 kilometers. And similar with tail dependence coefficients, we have this decreasing pattern, so dependence is weaker with distance. The model has quite good fit. Of course, we have a lot of variability in data because we only have 60 months in total. So that's why we don't have that many points here. So yeah, but the fit is quite good. So the second example, we consider stock return data, monthly minima of the daily stock log returns from the S&P 500 index, and we include data from 3 sectors here: industrial machinery, electric utilities, and regional bank sector. We use period of time 2000 to 2019, 20 years, but we're going to exclude the period of time between 2007 and 2009, which corresponds to US prime mortgage crisis, just to remove this period of volatile markets. So the link in Copulas, again, the same, reflected Clayton with different parameters now. We have the correlation matrix, which has the factor structure. So essentially, we assume they have 2-factor structure if variables are from the same sector, and 1-factor structure for variables from different sectors. So dependence is stronger if variables are from the sector, because you have 2 factors to model this dependence in this case. So again, we fit this model, and we have pairs of stocks from sector 1, sector 2, and sector 3 on the top, and pairs of stocks from sectors 1, 2, 1, 3, and 2, 3 in the bottom of the picture. And you have a Spearman's row for different pairs, and you see that black dots are empirical estimates observed from the data, and green dots are model-based estimates. So the estimates predicted by model. And you see it's they're quite in good agreement. So they match each other. So the model fits well according to this data. Similar with top-up tail dependence coefficients, if we estimate coefficients from our model, and then we compare against the empirical estimates, which are black dots, you see also a very good match between empirical and model-based estimates. Okay, so I think I should conclude now as I run out of time. So in this talk, we considered extreme value limits of 1-factor copulas with residual dependence, which is modeled by a normal copula. So these extreme value copulas are very flexible models for multivariate extremes, and they can be used to model different types of dependencies when you with the property selected linking copulas and the correlation matrix sigma. In particular, you can model spatial extremes, or you can model data with factor structure. Estimation is feasible in high dimension as well for this class of models, and many popular models in statistics are special cases of this class of models. Okay, so here I want to conclude, and here's the link to the manuscript, which is available on arXiv. So this is the link to the manuscript, so if you're interested. And thank you very much for your attention. So this is also some literature that I used in my talk. Okay, thank you.
Thanks, Pavel. That was a great presentation and
thank you.
Good result. Are there any comments or questions for Pavel? Robert, go for it, Robert.
Great. So there's also, I don't know much about this subject, but so it permits me to ask a question with no worries. But there's multivariate extreme value copulas, and there are multivariate extreme value distributions, not necessarily copulas. Correct. Why do you choose a copula framework instead of using just a multivariate distribution?
Correct. So yeah, it's a good question, actually. I would say it's kind of, we have 2 alternative methods of constructing multivariate extreme value distributions. And Copulas is just one way to construct a flexible multivariate extreme value distributions. So you just start with some copula, then you consider extreme value limit of this copula by taking component-wise maxima, and then you get a copula. So essentially, multivariate extreme value distribution and copulas, they're very similar concepts, because in both cases, you kind of have fixed margins. For multivariate extreme value copula, well, if it's a copula, of course, it has uniform 0-1 margins. But for multivariate extreme value distribution, it's a distribution with fixed margins as well, but they're not uniform, but they're free-share ones, okay, because it's a univariate extreme value distribution. So in some sense, it's kind of two alternative ways to think about this problem. So you can try to start with the distribution of component-wise maxima, not necessarily a copula, and then try to derive the extreme value limit. Or you can work on a copula scale. So you can start with the copula instead, and take the limit, and you consider what kind of limiting distributions you may get.
So what I was interested in was the relative advantages or disadvantages of both approaches. Now, for example, I don't know much about extreme value stuff, but for example, with the generally in Copulas, you get consistency with fitting a marginal distribution.
Mm-hmm.
Now, I suppose you take a linear combination of the components, and then the multivariate will also give you some implication for the linear combination of components about what it's like. So I'm just interested in the various properties of one approach versus the other approach.
Well, they are kind of, in some sense, they're kind of equivalent.
Well, they're not equivalent. I mean, think of a mixture of normals, and okay. Now if you fit a mixture of multivariate mixture of normals, then the implied marginals, if you've got a high dimension, are not gonna necessarily be good estimates of the marginal distributions.
Mm-hmm.
Whereas if you do a copula of that, then the marginals are going to be the marginals that you fit directly to each component. Mm-hmm. So, that's an illustration with a mixture of normals. If you've got something with 10 dimensions, you're going to have each component having 10 by 10 covariance matrices.
Correct.
So that's why I'm interested in just the two approaches and what they give you. They're not equivalent by any means in lots of situations.
No, what I'm talking about is like the extreme value. If you take extreme value, if you construct extreme value distribution as a limit, then you can start with the copula, or you can start with some underlying distribution and take the limit. But of course, the from practical perspective, copulas offer a lot of advantages. Absolutely right. For example, yes, computing fitting the distribution with the desirable margins is one of them. I agree, and you can avoid multiple problems when fitting multivariate distributions to high-dimensional data, because you can actually split the process into two parts. You can fit the copula to model the joint dependence. You can separately model the margins. You can combine them together to get a flexible distribution. So yes, that's definitely an advantage.
What's the downside?
The downside?
Yeah.
Of copulas?
Yeah.
I'm not sure if they have any downside. So the problem with copulas, though, that's it's hard to find a good model. So it's not that easy to construct a very flexible copula, because all the copulas, like there are many copulas available, are not very attractable in high dimensions. So some copulas might have few parameters, but they're not very flexible, because they may assume that the dependence is kind of symmetric or exchangeable, like Archimedean copulas, and they cannot be used to model data with heterogeneous dependence. Some other more flexible ones might be very difficult from computational perspective. It might be difficult to apply them to high-dimensional data sets. So, for example, comparing to multivariate normal models, I would say the main drawback of copulas that you cannot easily extend them to very high dimensions. So you really need to develop some computational tools fit models to really big data. Right now, you can do it with hundreds variables, maybe 1,000 as a maximum. But if you try to fit it to 1 million, perhaps you're not gonna make it. So they're computationally more intensive. That's true, compared to normal models. So I would say it's maybe a major drawback. But we just need to consider some estimation methods for copulas in high dimensions. This is actually some projects that I'm working on, and there are some promising results that actually for factor models, the class of copulas that have this factor structure with the common factor involved, it might be possible actually to get a very decent estimates of copula parameters in high dimensions, approximately, which are very decent estimates, and that would help to actually extend this model to very high dimensions. But this is work in progress still.
Pavel?
Yep.
Okay, thanks very much.
Yeah, okay, thank you.
Yeah, there's also a question from Artem.
Yes, thanks. So I can see the point of modeling high dimensions, but are there results that would suggest a form of denseness to factor copulas, in the sense that you could approximate or model any type of dependence using them? Do you see what I mean? So
yeah.
Are there results that would suggest the fact that copulas allow you to model comprehensive copulas?
Yeah, so yeah, I think I understand your question. So I think the answer is yes, but I haven't proved it yet. So the more I study factor models, the more I'm convinced that actually you can approximate any models with the factor structure. But it's a question of how many factors you have to select. So sometimes you may consider multi-factor models when you have actually infinitely many factors and they're kind of mixed together to obtain a very flexible distribution. And well, one example is a convolution model when actually you integrate over multiple factors and you get a joint distribution. So it becomes a multi-factor model. It's not just a single factor, but you may want to consider a 2, 3, 4, or even infinite number of factors. And I would say that if you increase the number of factors in your model, you would be able to approximate pretty much any copula.
Yeah, I can see that happening. I wonder if there's a formal result of that.
Unfortunately, not yet. So it's a bit tricky. So it's still work in progress. Would be nice to get that, but haven't formalized it yet. No,
I see. Thanks.
Yeah, no worries.
Pavel, I have a question on behalf of Nan. The question is, if we have no knowledge at all of sigma, then can we still estimate sigma and theta together?
So yeah, so it depends on applications. So it's a good question. So let's say we don't know linking copulas, right? So you remember that in the model, let me maybe just go back a little bit. So you have a few important building blocks, right? So you have the linking copulas. So to use likelihood approach, of course, we assume that we know linking copulas. And here we also have the conditional normal, and then we have some sigma matrix, which has certain structure, but we don't know what structure sigma has. And it's a good question, and actually it might be possible to make inference on the common factor and the linking copulas. So the idea here, for example, if you have a conditional independence model, so when you condition on the common factor, it might be possible to recover the common factor itself and the linking copulas non-parametrically. So there are some methods actually that would allow you to estimate the linking copulas, so you don't have to select some arbitrary copulas. And I guess similar approach can be adopted to the general class of models when you have conditional normal. So when you actually can estimate the correlation matrix sigma. Again, this is work still in progress, but some results again already look promising. So it's not just, yeah, so it's important that we know the structure here. And of course, some applications might assume that the structure, you may have spatial structure when you model spatial extremes. If you have a group structure when you model financial data, but sometimes it's not clear what structure you have to select for sigma. And there are some diagnostic methods that are possible that you can use to decide what structure is more appropriate. But there are many interesting topics here. Unfortunately, I haven't finished it yet. But there are some non-parametric estimates available in the class of factor models when you can recover linking copulas. And I guess the same true for the conditional normal copulas when you also can recover the structure of sigma matrix as well. Okay, so does it answer?
Thanks, Pavel. Maybe before we wrap up, I have like a question. It is like, so these Copula models that you propose are flexible. Could you even make it more flexible by saying instead of being conditionally normal, they could be conditionally T, or considering more than one common factor? Would that be useful?
Well, yes and no. For student T, definitely, but T itself already is a factor model, right? So it's conditional normal itself. So maybe it doesn't make sense to condition, because already when you use T distribution, it's already conditional normal. But if you say you want to add more factors, then you can simply use sigma matrix, which has a two-factor structure instead of one factor. Because otherwise, you see what happens if you have one factor, like in this slide, you have one-dimensional integration. If you want to consider a conditional normal copula after you condition on two factors, you would have to integrate both factors out. So you get a two-dimensional integral, which is already not very tractable in high dimensions. However, you can instead condition on a single factor, V naught, but then you assume that sigma itself has a one or two factor structure. Then the resulting model can be seen as an extreme value limit of a two or three factor model. And you still need only one-dimensional integral to estimate the density. So in some sense, models with more than one factor can be obtained if you select sigma matrix with a factor structure here. But in general, I think it's an interesting question to consider maybe a different conditional distribution, not the normal copula, but something else. So I think this is definitely might be a good topic of future research.
That's what I was thinking. I was also thinking of like if you wanted like imagine I don't know, skew normal distribution. But I guess you can, as you say, using the sigma, you can probably get it because the skew normal is going to be constructed on the normal.
You don't really need skew normal because skew normal, you get it to get asymmetry, right? But if you select asymmetric linking copulas, C1 naught, CD naught, then the resulting copula on the slide, C1D, is going to be asymmetric. So you don't need to worry about skewness, really. If you select skewed linking copulas, then the resulting distribution is going to be skewed. And well, of course, the extreme value copula is always skewed. It's not symmetric. But this is something that would be nice to investigate in any case. Maybe some special case of normal, yes, skew normal, skew T, or maybe some simple multivariate distributions like Frank copula or something like that. So it might be interesting indeed. So yeah, so it could be a good topic for future research.
Yeah, and then you could compare. You could compare the performance of different models on specific examples.
Yeah, that's true. Absolutely.
Yeah, cool. No, that's good. Are there any final questions or comments for Pavel before we wrap up? I think we've kept you under questions for quite some time. So thanks again, Pavel, for agreeing to give a talk and for delivering a good talk. And yeah, the seminar was recorded and will be put on the blog relatively soon.
Okay, that's good. So maybe I just go back to this slide with the link. So if you want to download the paper, where is that? In the end, yeah, this is the link. So if you're interested to check more details, yeah, you can check this paper on archive.
Thanks, Pavel.
Okay, thank you. Thanks a lot for very nice questions and for inviting me to give this talk. And yep. So,
good, that was great. People are saying thank you in the chat.
Yeah, thanks a lot. Thanks for all good questions and thanks for attending. Okay, so we can.
Yeah, I'll send you an email, Pavel, once I have once I've put it on the blog, so you have the link.
Oh, excellent.
Talk
Thanks.
if you want to use it.
Excellent. Okay, so then I can close the window now, right?
Yeah.
Okay.
Yeah.
So okay, thanks again for inviting and.